In the chem activity number 11 and the associated videos, we will continue our exploration of stereoisomers, and in particular, our investigation of enantiomers, chiral molecules, and the various conventions and representations of such molecules. To begin with, let's turn our attention to a molecular representation of a chiral molecule. In this video, you can see that we have a ball and stick model representation of a molecule. This molecule is called glyceraldehyde. It is indeed chiral. You can see that a mirror is being held up so we can see its mirror image. And then what's going to happen is the mirror image is going to be removed, and we see, in fact, here is a molecular representation of the mirror image. In other words, it's an enantiomer. And to reinforce the idea that an enantiomer is a mirror image that's non-superposable, we'll pick up this other molecular structure, ball and stick, and try to superpose, and you can see that they're not superposable. They are indeed different molecules. So let us return back to the notes and to teaching model number 1. In teaching model number 1, we have representation of 4 different molecules. You can see that some of them are labeled chiral and some not chiral. Recall that we established earlier that a great way to determine whether or not a molecule is chiral is to see that it does not have a plane of symmetry. And in turn, a non-chiral molecule will have a plane of symmetry. So for instance, in those molecules that we've labeled as not chiral, they all have a plane of symmetry. A plane of symmetry. And again, notice that we've got 2 hydrogens. We run a plane running right through the molecule, kind of orienting this way. We can split the molecule completely in half, and that would be a plane of symmetry. In a similar way, we can divide this molecule right down the methyl group through to the oxygen, a plane of symmetry. Whereas the other molecules represented, the first one and the third one, do not have a plane of symmetry, and therefore they are chiral. Now, as it turns out, the usual cause of chirality for a molecule is the fact that it has at least one asymmetric center. That's also called a chiral center. And a chiral center or asymmetric center is an example, a specific example of a stereocenter. A chiral center is an atom that has 4 different groups attached to it. By convention, we'll often represent a chiral center, if we want to show that it's there, with an asterisk. Now notice this last point. A molecule with one chiral center is always chiral. Perhaps you get a sense that if there were more than one chiral center, in other words 2 or 3 or 4, we have to investigate further to see whether or not the molecule is chiral. But if there's only one chiral center, that molecule is indeed chiral. Before we go on to the first of the key questions, I just want to emphasize what we mean by 4 different groups. So in our structure on the left here, you can see that we have a methyl group, an alcohol group, we have hydrogen, and then D represents deuterium, which is the more heavier isotope of hydrogen. That's sufficiently different, that is to have an extra neutron in the nucleus, to make that group different, and indeed that molecule would be chiral. In the other example, note that we have a hydrogen coming off of our chiral center, we have a CH3, and then we have CH2 and a CH2. And at first you might say, well, that's the same. But in order for it to be the same, it has to be completely the same, however long the chain is. So in order for us to say that the groups are the same, they have to be exactly the same. As a case in point, in our 4th molecule here, we do have a hydrogen, we have a methyl group, and then we've got the CH2s and the CH2s, and then you keep on going, another set of CH2s, and then the oxygen. They arrive at the same spot. So in other words, this carbon here is not chiral. It does not have 4 different groups attached to it. So with that little bit of introduction, let's take a look at the key question number 1. So here you have a series of molecules, and you're asked to do 2 different things. For one, you're asked to mark with an asterisk any chiral center. Further, you're asked to circle those molecules which are chiral. So I encourage you to stop the video and give this a try. So in terms of those atoms which are chiral, let's mark the asterisks. So you can see that it is possible for a nitrogen to be chiral, but this will be a cationic nitrogen where there are 4 different groups attached. Do compare your answers to the ones that are provided here, and be sure that you understand why there are 4 different groups attached to each of the carbons that I've marked with an asterisk. In terms of those molecules that are chiral, here they are. So in the top 2 examples, as well as the one on the end here, there's only 1 chiral center in the molecule, therefore that molecule will be chiral. In the bottom row, we have some examples of molecules with 2 chiral centers, and indeed this one and this one are also chiral. Now we know that they're chiral because they do not have a plane of symmetry, whereas this structure right here, although it does have 2 chiral centers, there is a plane of symmetry, and therefore this molecule is not chiral. It has a mirror image, but the mirror image would be superposable. So in a sense, you're using 2 things to kind of monitor whether or not you'd expect a molecule to be chiral and have an enantiomer. You're looking for those chiral centers, but you're also looking for planes of symmetry. So I'll just remind you, this one has a plane of symmetry.